Hello, everyone. Welcome back to Calculus. So today, what we are going to be doing is we're going to be learning about what are called the first and second derivative tests. So these are going to be utilizing sort of the information that we figured out in the last couple of videos about how the first and the second derivative are related to the shape of the graph of f. We're going to be kind of taking that information, and then we're going to be trying to use that information to sort of pinpoint how that is then related to the maximums and the relative maximum and relative minimum of a function. So kind of taking our knowledge of first and second derivatives, how they relate to the shape of f of x, and just pushing it like one step further, trying to figure out stuff about relative max and relative min. So want to think through sort of an example first and think about sort of the intuition that's going to go behind the first derivative test. So we're given the graph of f of x, and the question asks us, what can we say about f prime of x near the maxes and mins of f of x? So I want to think about sort of these 3 points are going to be the maxes and mins that I can see. The question is asking me, what can I say about f prime of x near these? Interesting. Okay. Well, let's see. So near this first point, let's see, f prime of x seems to be positive over here, or increasing, and then f prime of x becomes negative after. So right before my relative max, I have that f prime of x is positive, and right after, I see that f prime of x goes to negative. And that makes sense, right? I'm increasing to get to my relative max, and then I need to decrease after relative max. And so it makes sense that f prime of x would be positive, and then it would go to negative, because I need to go from increasing to decreasing. Okay, cool. And then similarly, if I look at the other relative max, I actually see the exact same thing. F prime of x is increasing right before the relative max, and then, sorry, f prime is positive because f is increasing, and then right after the relative max, f prime of x is negative. Okay, so I have the same pattern with the maxes, and then I'll have the flipped pattern at the min. So right before the minimum, f prime of x is going to be negative, and right after the minimum, f prime of x is going to be positive. Okay. And again, sort of, this is just one example, but any graph that you play with is going to have this sort of, this happening as long as your derivative is defined. So before maximums, you're going to be increasing, and then after maximums, you're going to be decreasing. So f prime is going to be positive, and then switch to being negative. And then around minimums, f prime is going to go from being negative to going positive. And so that is really just what the first derivative test says, just in sort of more careful language. So if f prime changes sign from being negative to positive at x equals c, then we are going to have a relative, that is not correct. So sorry, f prime is negative to positive, we're going to have a relative minimum. Sorry about that, of f of x. And then if f prime goes from being positive, in other words, f is increasing, to negative, so f is now decreasing, then we would get a relative maxima of f of x. So that is the first derivative test. F prime is negative, then positive, relative minimum. F prime is positive, then negative, we get a relative max. Okay. So let's see an example of this in particular. So we're given that f of x is x to the 4th over 4 minus 7/3 x cubed. We want to find and classify all the relative extrema, so all the relative maxes and mins. So first of all, I'm going to relate it to f prime of x. So f prime of x should be, let's see, if I bring down my 4, then my 4x cubed over 4, the 4's cancel, so I'm left with x cubed. And then minus 7x squared. That's going to be my f prime of x. And again, I want sort of to figure out the sign chart of where f prime is going to be positive and negative. So I'm going to want to figure out where this thing equals 0. So it's going to make sense to factor f prime of x. And that helps me start making my number line. So at x equals 0 and at x equals 7, f prime is going to be 0. And then I can do my test points. So let's see, I'll test x equals 1, x equals -1, and x equals 10. I'll go ahead and test those into f prime of x. When you do that, you'll get, let's see, a negative value, a negative value, and then a positive value. And so now we want to use this information and we want to classify our relative extremas. So we had f prime go from negative to 0 to negative. That wasn't in the first derivative test. So that's kind of interesting. Let's think about what that means for a second. So f prime is negative, so my function is like decreasing. And then there's a moment where the derivative is 0. And then my function goes back to decreasing. So it looks something like this. So I don't end up with a max or a min. I just kind of basically like have a pause in my decreasing is all that happens. So nothing super exciting is happening at x equals 0. But at x equals 7, we go from decreasing, because f prime is negative, to increasing, since f prime becomes positive. And so by the first derivative test, we get to say that there is a local minimum or relative minimum at x equals 7, just by interpreting the fact that f prime goes from negative to positive. Okay. So that is an example of implementing the first derivative test. You're just going to go through, find your signs of f prime, and then interpret changes in the sign of f prime. I do want to note that endpoints can be kind of tricky if you're looking at a closed interval. So again, this is the first derivative test repeated with the typo repeated. So these are the two things that we saw earlier under the first derivative test. And I just want to note that we need to be careful with endpoints if we're looking on a closed interval. So for example, so just the first two sort of lines in here help me find maxes and mins in like my full picture of my graph. But if I look at just a closed interval and I restrict myself to just looking at, say, from, let's do here to here. So just looking at that as a closed interval, that means basically I need to think about sort of deleting part of my graph. Sorry, I'm gonna delete it this way. So I'm not gonna think about, no, I don't want that. Sorry. Let me do my closed interval being from here onward. So if I think about sort of deleting my pieces of my graph that aren't relevant, and just thinking about sort of the relevant part of my graph, so say the red part of my graph is the only part that I really want to talk about doing the maxes and the mins on. Then it's interesting to note that this point is now a relative minimum of my red picture, even though it wasn't a minimum of my full function. But basically, I've sort of cut off part of my graph and I've created a new minimum by cutting my graph at kind of a weird point. And so that's what this note is about, is that you might need to think about your endpoints if you are thinking about just part of the graph rather than the full graph. So let's go ahead and think about an example of what that means. So I'm taking that same function f of x, and I'm going to just think about it on a particular interval. I'm going to copy over my work from last time since it's all going to be relevant. Okay, so my function is the same, so I get the same f prime. And then my number line, instead of thinking about it going off to infinity, I'm just going to cap it between -1 and 1. So I'm going to not have the full interval, but instead my interval is going to stop at -1 and go up to +1. So I'm not going to have everything. In particular, I'm not going to have like the 0 that was at x equals 7, but that's fine. So I'm now just thinking about sort of this part of the interval, or of the function. Basically, all I've done so far is I took our work from earlier and deleted the extraneous stuff, deleted everything that was outside of -1 to 1. Okay, and so my question is, where are all the relative extrema on this now closed interval? And so we don't get to say any relative extrema coming from the first derivative test directly, because again, we would need a change in the sign of f prime, and we don't see any changes in the sign of f prime. But I do need to think about my endpoints. And remember, we talked earlier that this, since f prime is negative, then it kind of levels out for a moment and then becomes negative again. My graph of f is going to look something like this. This being -1, x equaling 0, and x equaling +1. We're going to have this going on. And so if you think about that, with this shape, that means that on this closed interval, we're decreasing more or less the whole time, other than that moment where we kind of level out. So there is going to be a relative max when we started. So at x equals -1, so that's going to be the highest point in our graph, and a relative minimum at x equals +1, because we're going to be increasing. Can't quite write in that little corner. Okay, so function is sort of decreasing, levels out, decreasing. And so we're going to have our maximum at the left endpoint, so at x equals -1. And then we're going to decrease until we get to our minimum, which is going to be happening at x equals +1. So this isn't really quite the first derivative test, but really just thinking about our endpoints and thinking about what f prime is telling us is happening at those endpoints. Okay, so that's something to just be sort of mindful of if we ask you to classify relative extrema on a closed interval. You need to do the first derivative test sort of everywhere inside of the interval, and then you also need to think about your endpoints and what's going on there. Okay, so that was the first derivative test. So basically we said that if the sign of f prime changes, then you're going to have a relative max or relative min. Turns out we can also think about the second derivative test, meaning relating sort of f double prime of x to the maxes and mins. So let's go back and think about an example. So that same example from earlier, where we want to think about the maxes and the mins of our function. And we want to think about what's going on with f double prime of x. So let's see. At this maximum, we see that f of x is concave down like a frown. So if you remember, that means in this region, f double prime of x is going to be negative. We're down, concave down like a frown. around the relative minimum, the graph of f is concave up like a cup. And so in this region, we're going to have that f double prime of x is positive. And then around this maximum, or again, f of x is concave down like a frown. So I know that f double prime of x is negative again. And it seems like we're starting to see a pattern. And again, you can play with other examples, and you'll see that at relative maxes, you're going to have that f double prime is going to be negative, and at relative mins, you're going to have that f double prime is positive. So that is sort of one part of the second derivative test. But just remember, just because f double prime is negative, that doesn't mean we're definitely going to be at a relative max. So for example, in this whole region, right, we're concave down like a frown. And so at all of these points, you could say that f double prime is negative, but they're not all relative maximums. So we are going to have to think about it a little bit further than just saying, oh, if f double prime is negative, then we have a relative maximum. It's not quite that simple, but it's close to that simple. We just need to add in a little bit more information. And so that's kind of our intuition behind the second derivative test. And then here is the full second derivative test. So if we have a positive f double prime and the first derivative equals 0, so positive f double prime, that says we're up like a cup in that region, and f double prime equaling 0 means that, or sorry, f prime equaling 0 means we really are at sort of the bottom of the concave up region. So based on that picture, we seem to have a relative minimum of f of x, and that is indeed what the second derivative test says. On the other hand, if we had a region where f double prime was negative, so we're concave down, and in particular, we highlight the point where f prime equals 0, then that x value is going to be a relative maximum of f of x. So to do the second derivative test, we're going to need to check the sign of f double prime at places where f prime equals 0. And again, same caveat of if you're looking on just a closed interval, you're going to need to be careful with your endpoints in the same way that we were earlier. Okay, so let's see an example of this. So we are told that f of x is x to the 4th over 4 plus x cubed plus 2. We want to find and classify all the relative extrema of f of x. So let's see. So I'm going to need f prime of x, which is x cubed plus 3x squared. And I'm going to need f double prime of x, which is then 3x squared plus 3x. And so I need the sign of f double prime of x wherever f prime of x equals 0. So I'm going to go ahead and solve for where f double prime, or where f prime of x equals 0 by factoring. So that says that I care about x equals 0 and x equals minus 3. So f double prime of 0 equals 0, and f prime of minus 3 equals 0. Okay, so then the other part of the second derivative test was looking at the sign of f double prime at these places. So since f prime of 0 equals 0 and f double prime of 0, let's see, that's going to be 3 times 0 squared plus 3 times 0, so that equals 0. That's neither positive or negative, so we really don't get to say anything. Second derivative test won't tell us anything. Test does not say anything about x equals 0. Okay, so we've checked sort of one place. All right, and then the other place that we had that the first derivative equals 0 was f prime of minus 3 equals 0. And then let's think about f prime at minus 3. So x equals negative 3 in f double prime. So f double prime of minus 3 is going to be 3 times minus 3 squared, so 27, plus 3 times negative 3. Okay, so we're going to get 18 there. So this is going to be positive. So at negative 3, f prime is 0, and f double prime is positive, so we're concave up like a cup. And so we're looking at a relative minimum. So the second derivative test tells us that x equals minus 3, or there is a relative minimum at x equals minus 3. Okay, so this is going to be our process for the second derivative test. You're going to find out all the places where f prime equals 0, and then you're going to look at the sign of f double prime in those places and interpret it according to the second derivative test. Okay. So now we have two different tests that can both tell us about the relative extrema of our original function. Either test is going to be valid in sort of any given situation. Sometimes one test might be easier than the other, just depending on how hard it is to take the derivative and whatnot. But a lot of times it's pretty equally easy to apply both tests. So along those lines, go ahead and try it yourself. I want you to look at the function f of x equals x cubed plus x squared plus 2. And I want you to find and classify all the relative extrema of f of x using the first derivative test, and then do it again using the second derivative test and make sure your answers match up. So go ahead and pause here and try doing the first and the second derivative tests for this function. Okay. Hopefully you did pause and try that. And what you should be seeing is that you're going to get a relative maximum at x equals minus 2 over 3, and a relative minimum at x equals 0. And that should be your full amount of relative extrema that you can find using either the first or second derivative tests. All right, awesome job, y'all. See you next time.